For centuries, astronomers believed our solar system was mostly quiet, with only the rarest of objects wandering in from the interstellar void. But in the story behind New Objects Are Multiplying as 3I/Atlas approaches Mars, that old certainty has just been shattered. In mere days, clusters of asteroids have raced past Earth, an amateur's telescope has caught a newborn comet flaring into view, and, most improbably of all, 3I/Atlas, only the third known interstellar visitor in recorded history, is now streaking toward Mars. If space was once thought to be empty, why is it suddenly teeming with cosmic arrivals? And what does it mean that we're just noticing now? The answer is more urgent and unsettling than you might guess. It's difficult for us to truly grasp the emptiness of space. Our solar system, with its planets and moons, feels like a crowded neighborhood compared to the vast, silent gulf beyond. Out past the reach of the sun's wind, more than 18 billion kilometers away, Voyager 1 and Voyager 2 are the only human-made objects to have crossed into interstellar space. For decades, astronomers waited in vain for any sign that something might come the other way. The first hint arrived in 2017, when a faint, elongated body, later named Oumuamua, swept through at a speed and trajectory no solar system object could match. Just 2 years later, 2I/Borisov appeared, a true comet with a glowing tail, and confirmed that the solar system's borders are more porous than once believed. These were not just rare events, they were unprecedented, separated by all of human history until now. Most years, not a single confirmed interstellar visitor is detected. The silence between these discoveries has been the rule, not the exception. That's why the sudden arrival of a third, 3I/Atlas, within less than a decade defies old expectations. For generations, the sky seems stable and predictable. Now the numbers suggest we may have been looking through a keyhole, missing visitors from the dark between stars. When the quiet is broken, it's a reminder that the universe is less settled than we imagined. The rare becomes possible, and the possible becomes a question. What else might be out there, waiting to be seen? In the first week of August 2025, 5 asteroids swept past Earth in just 3 days, each one closer than the Moon. The smallest, no wider than a city bus, was first flagged by a survey telescope in Arizona. Within hours, NASA's Planetary Defense Coordination Office was in round-the-clock contact with observatories worldwide. The official distance for a lunar close pass is 384,000 kilometers. All 5 objects crossed that threshold, some slipping by at less than 100,000 kilometers, barely a quarter of the way to the Moon. Each new detection meant a fresh round of calculations, with analysts at JPL and NASA debating whether to issue public alerts. The tracking window for these objects rarely stretched beyond 72 hours, putting the system under real-time pressure. Conference calls ran late into the night, with team members weighing the risks and reviewing incoming data from radar and optical tracking. Some argued for immediate public notification, while others urged caution, citing the object's small size and low impact probability. The tension was not just technical. Internal logs describe a sense of vulnerability, knowing that had any one of these asteroids been on a different trajectory, warning time would have been measured in hours, not days. The episode served as a stress test for planetary defense protocols, exposing both the strengths and the gaps in current surveillance. For the analysts on those calls, the cluster of near misses was a stark reminder that Earth's safety net is only as strong as its weakest link. The stakes had never felt more real. On the evening of September 5th, a new message began circulating through astronomy forums and group chats. Vladimir Bezugli, an amateur observer working from his home in Ukraine, had noticed a faint, unfamiliar smudge in the latest Swan all-sky images, public data from the SOHO spacecraft's solar wind anisotropies camera. Within minutes, he posted coordinates and a cropped mosaic to a global alert list, inviting others to check his find. As word spread, telescopes across Europe and beyond turned skyward. In Spain, a seasoned coordinator rallied local hobbyists, some using backyard setups with homemade spectrographs and hastily assembled tracking mounts. The next few hours became a blur of activity. Images uploaded, positions measured, and reports compared in real time. Weather and equipment glitches forced improvisation. A laptop borrowed from a neighbor. A telescope lens cleaned with a t-shirt. By midnight, 2 Spanish observatories, Monsec and San Bartolomé, had confirmed the new object. Their CCD images, matched to Swan's coordinates, showed a diffuse glow at magnitude 8.7, brighter than most comets at discovery. Professional astronomers joined the effort before sunrise, relaying higher resolution data from observatories in Chile and the Canaries. The Minor Planet Center issued a provisional designation, C/2025 R2, Swan, less than 48 hours after the first alert. In the days that followed, the comet brightened rapidly, with forecasts hinting at naked-eye visibility by late October. For the global network of amateur astronomers, the discovery was proof that even in an era of automated surveys, a sharp eye and swift collaboration can still bring the cosmos a little closer. On July 1st, 2025, the Atlas survey team in Hawaii began their nightly sweep, 800 images, each one a potential doorway to something new. That night, an unfamiliar speck appeared in the data. John Tonry and Larry Deneau, leading the shift, double-checked the detection. The object wasn't just fast, it was on a path no solar system body could follow. Calculations poured in. Its orbit was hyperbolic, with an eccentricity near 6. In astronomical terms, that's a one-way ticket from interstellar space. Most comets and asteroids are bound by the sun, looping in ellipses. This one was different. Its incoming velocity alone, calculated at over 58 kilometers per second, ruled out any origin from our own backyard. The team's adrenaline spiked. Raw images and orbital solutions were sent out to the Minor Planet Center in Massachusetts for rapid confirmation. Within hours, the MPC issued a circular. This was not just another comet. Its designation changed from a provisional string of numbers to 3II/Atlas, the third confirmed interstellar object ever recorded. The news raced through astronomy circles. Slack channels and email threads lit up with urgent questions. Was the orbit real? Could it be a false positive? Every pixel was scrutinized, every calculation redone. Early spectra arrived from follow-up telescopes and brought another surprise. Unlike Borisov or typical solar system comets, no gas emission lines appeared. No CN, no C2, no water. The coma was dust only, glowing faint and red with a featureless continuum. That, too, set it apart. The combination of trajectory, speed, and spectral signature left no room for doubt. 3I/Atlas had slipped into our solar system from the dark between stars, a true wanderer caught in the act. Alan Harris, a veteran asteroid dynamicist, looks at the recent burst of discoveries and finds the timing hard to accept as mere chance. At the 2025 symposium, he points out that such tight clustering, 5 close asteroids in 3 days, doesn't fit the statistical models, even when accounting for survey gaps. Harris argues that if randomness alone explained these events, we would expect longer waits between clusters, not a sudden stack of close shaves. David Farnokia, a leading orbit analyst at JPL, takes a different view. He highlights the sensitivity curves of modern surveys, showing that as telescopes scan deeper and more often, they naturally catch more objects in quick succession. Farnokia's simulations predict these spikes, especially during periods of clear weather and coordinated follow-up. The numbers, he says, track with our improving tools, not with a sudden cosmic influx. The debate remains unsettled, with both sides agreeing only on one thing. The data is forcing astronomers to rethink what counts as normal in a sky that now seems anything but quiet. Policy analysts at the Government Accountability Office have warned that delays and cost overruns in the NEO Surveyor mission are leaving gaps in our early warning network. Originally budgeted at under $600 million, the project now carries a price tag of $1.2 billion and won't launch before mid-2028, 2 years behind the congressional mandate. Meanwhile, the Vera C. Rubin Observatory is set to triple the discovery rate of near-Earth objects once it begins operations, promising over 10,000 new finds every year. Some theorists speculate about links between recent object clusters and the sun's passage through the local interstellar cloud, but there's no confirmed evidence. For now, the lesson is clear. As the sky grows busier, the real risk isn't what we see, but what we might still miss. We're finally paying attention. In just a few weeks, astronomers recorded 5 near-Earth asteroids within lunar distance and confirmed 3 Atlas as only the third interstellar object ever tracked in our solar system. These events follow decades of relative quiet, breaking patterns first documented in the early 20th century. While experts like Alan Harris highlight the improbability of such clustering, others, including David Farnokia, point to improved survey sensitivity as a key factor. Official reports, such as the 2024 GAO review, note that missions like NEO Surveyor face delays, even as new objects multiply. To date, no direct link explains why so many discoveries arrived at once, and the origins of 3I/Atlas remain under investigation. What is certain, our ability to detect and respond to celestial visitors is growing, and the sky above is more dynamic than records ever suggested. The evidence is clear, space is busier, and for the first time, we are truly watching.